More than half of all the electricity generated worldwide is consumed by electric motors, and most of them are induction motors. They drive everything from industrial machinery and pumps to ventilation systems, compressors, and countless manufacturing processes. In this video, we'll follow every major manufacturing step, from the rotor and stator to the final assembly, while uncovering why this motor can produce torque without any electrical connection to its rotating shaft. Manufacturing begins with the rotor shaft. A solid alloy steel bar is first cut to length. Its high strength and resistance to twisting allow it to withstand years of continuous operation. The shaft is then precision machined on a CNC lathe, forming the bearing seats and mounting surfaces required for the rotor assembly. After every critical dimension and rotational runout have been verified, the shaft is ready to receive the rotor core. The rotor core begins as thin sheets of electrical steel, each coated with an insulating oxide layer. This coating electrically separates the laminations, limiting eddy currents and reducing heat inside the rotor. In the first stamping operation, circular blanks are cut from the steel sheet. A second die then punches the central opening and the internal slots that will later form the rotor's conductive cage. The finished laminations are now ready to be stacked around the rotor shaft, forming the magnetic core of the rotating assembly. The steel core itself does not produce torque. It provides a low reluctance path for magnetic flux. As the laminations are stacked, their slots form continuous channels along the rotor. These channels will later be filled with aluminum to create the squirrel-cage, the part that ultimately produces the turning force. That squirrel-cage is formed by injecting molten aluminum alloy under high pressure. The alloy is selected for its high electrical conductivity, excellent fluidity, low shrinkage, and resistance to hot cracking, while remaining strong enough to withstand thousands of revolutions per minute. As the aluminum solidifies, it forms the conductor bars and end rings in a single casting operation. Together, they create a closed electrical circuit inside the rotor, the conductive structure where induced current will later generate the motor's turning force. The completed rotor core is now joined to the shaft. Before assembly, the shaft is cooled to temporarily shrink its diameter by a tiny amount. A hydraulic press then forces it into the rotor core, creating an extremely tight interference fit without the need for bolts or welding. As the shaft returns to room temperature, it expands and locks firmly into place, allowing both parts to rotate as a single unit. After the final machining process, the rotor is complete. 3 components now work as one. The steel shaft provides strength, the laminated core carries magnetic flux, and the aluminum squirrel cage forms the conductive path where induced current will later generate torque. The rotor is now ready to be assembled with the stator. Like the rotor core, the stator core is stamped from electrical steel laminations. In fact, both parts are often produced from the same steel sheet, with the larger outer section becoming the stator core. The laminations are now stacked to form the stator core. An automated welding system then permanently joins the stack, creating a rigid structure while preserving the insulating oxide layer between individual laminations. The completed core provides the magnetic path for the stator and serves as the foundation for the copper windings that will be installed next. Next, insulated copper wire is wound into precisely shaped coils. Each turn is carefully controlled to achieve the required number of windings, which determines the strength of the magnetic field produced when electricity flows through the stator. Every coil is made to an identical shape for consistent electrical performance before being inserted into the stator core. Before the coils are installed, each stator slot is lined with an insulating paper. This thin layer prevents the copper windings from contacting the steel core, protecting them from electrical short circuits. The preformed copper coils are then carefully inserted into the insulated slots, where they will later be connected to form the motor's 3-phase winding and generate the rotating magnetic field. With every coil in place, the windings are carefully positioned and secured inside the stator. Additional insulating paper is then inserted between the exposed end windings, preventing adjacent coils from rubbing against each other during years of continuous operation. The winding leads are now stripped, joined and connected into 3 separate phase circuits, matching the motor's 3-phase power supply. Each connection is protected with heat-resistant insulation before the windings are carefully laced and secured. This prevents the conductors from moving under electromagnetic forces and vibration during operation, helping preserve the insulation over the motor's lifetime. Together, these 3 stator phases will later generate the rotating magnetic field that drives the rotor without any electrical connection. Before assembly can continue, the stator receives one final layer of insulation. A liquid insulating varnish is drawn deep into the windings, filling the tiny spaces between individual copper wires. To see why this process is so important, let's step inside the factory's laboratory. After the varnish has fully cured, a sample stator is cut open and examined under a microscope. Magnified many times, the cured varnish can be seen completely surrounding the conductors, locking the windings together, improving heat transfer, and providing an additional layer of electrical insulation. Back on the production line, this process is performed on an industrial scale. Dozens of completed stators are loaded into a vacuum pressure impregnation system where they are immersed in insulating varnish. A vacuum first removes the air trapped deep inside the windings. Pressure is then applied, forcing the liquid varnish into spaces too small to be reached by surface coating alone. The stators are then transferred to curing ovens, where heat hardens the varnish into a solid insulating resin. Once cured, it bonds the copper windings into a rigid structure, reduces vibration, improves heat transfer, and provides an additional barrier against electrical breakdown. With the winding system now permanently sealed and reinforced, the stator is complete, ready to be paired with the finished rotor in the final assembly of the motor. Earlier, the rotor shaft was cooled to shrink before being pressed into the rotor. Now, the opposite happens. The motor housing is heated, so it expands slightly, allowing the finished stator to fit inside. As the housing cools, it shrinks tightly around the stator, locking it firmly in place. Every induction motor consists of just two main parts. The stator remains fixed, while the rotor is free to rotate inside it. Although they never touch each other, they work together to produce continuous mechanical power. Electrical power is supplied only to the stator. There are no wires connected to the rotor, making one question unavoidable. So how does it begin to spin? Inside the stator, insulated copper windings are placed into slots around the laminated steel core. When electrical current flows through these windings, they generate magnetic fields inside the motor. To understand what happens next, let's look at a simplified cross-section of the stator. The stator contains three separate groups of windings. These three phases are evenly distributed around the stator, each positioned 120 electrical degrees from the next. When three-phase AC power is applied, the current in each phase reaches its peak at a different moment. As one magnetic field grows stronger, the next one begins to take over. Instead of remaining in one place, the magnetic field continuously shifts around the stator. The result is a rotating magnetic field spinning inside the motor. As this rotating magnetic field sweeps past the aluminum bars of the squirrel-cage rotor, it continuously cuts across the conductors. The changing magnetic field induces an electric current inside the rotor bars. That current circulates through the aluminum bars and end rings, forming a closed circuit entirely within the rotor. The induced current generates its own magnetic field. As this field interacts with the rotating magnetic field produced by the stator, a turning force is created. The rotor is pulled around, accelerating until it follows the rotating field. This simplified animation shows only a basic two-pole motor. In real industrial motors, the rotor is built from hundreds of laminated steel sheets with cast aluminum bars, while the stator usually contains many more winding groups to create multiple magnetic poles. But the operating principle remains exactly the same. And that's why the rotor doesn't need any electrical connection. Energy is transferred entirely through electromagnetic induction. Back on the production line, the motor is ready for final assembly. The bearing end bracket is heated before assembly. Heating causes the bore to expand slightly, allowing it to slide easily onto the bearing seat. The end bracket is then bolted firmly to the motor frame. The terminal box is installed, providing a protected connection point for the three-phase power supply. A cooling fan is mounted onto the shaft to provide continuous airflow during operation. With every component assembled, The induction motor is now ready for testing before leaving the factory. Every electric motor begins as steel, copper, and aluminum. Through precision manufacturing and the principles of electromagnetism, these materials become one of the world's most important machines. If you'd like to explore the other side of electrical machines, you can also watch our video on how large electric generators are built and why they all run at exactly 50 or 60 Hertz.